All right, good morning, everyone. Welcome, everybody, to the third day of our Net Zero Research Conference. I'm Dr. Andy Smallbone. I'm an Associate Professor at Durham, and I'm the Director of the Decarbonisation of Heating and Cooling Network. And I'm going to be chairing today's session and tomorrow as well. The next 2 days are structured around the themes of the EPSRC network for the decarbonisation of heating and cooling. I guess the last 2 days have been principally about hydrogen, and particularly about hydrogen in for transport, but now we're moving over to heat and cooling more specifically. So over the next 2 days, we're going to be looking at the challenges across different sources of heating and the challenges faced by different sectors in meeting their net zero aims. I'll give you a quick explanation about what the network is, and then we'll move into the sessions. So we've only really recently launched the Network Plus on heating and cooling. And I guess the first question that everyone asks is, what is a Network Plus? So the UK research councils have established this kind of framework of Network Pluses. They've been created to provide an impact and dissemination platform for the many projects that the UKRI funds. They're extremely important mechanism for bringing UK industry together from academia all the way through to industry, in order to make sure that everyone knows that all of these hundreds of millions of pounds worth of projects, everyone knows that they're going on, and that information is shared. So what we've got is a dedicated team to organise dissemination engagement activities and support those projects. And we have other roles, like taking some kind of leadership role in leading what's happening in that particular area. And our challenge is the decarbonisation of heating and cooling. And I should also note there are other Network Pluses across challenges like transport, bioenergy, energy storage, etc., etc. The last 2 days have been about one of those in transport, which is obviously hydrogen transport technology. Who are Network Pluses for? Well, I think across these 8 different titles here, it's for everyone. Principally, I guess, about research and academia and people involved in technology and social science. But in general, actually, there should be an event funded through our network, which is relevant to everyone, all the way through to the general public. And in reflecting that, the fact that it's all paid for by UK Research Council, it's free for anyone who wants to attend our activities. There's no official membership, there's no membership fee, just sign up, come along. Obviously in lockdown, most stuff has happened in the online domain, but hopefully we'll be transitioning to face-to-face stuff in good time. The Network Plus is being led by Durham, Oxford, Brunel, Heriot-Watt, Leeds and Northumbria, and is supported and initially set up with lots of organisations supporting the application, but it's really for everyone. We might be leading it, but events and activities and speakers and so on, they're all from all over different places internationally and across the UK. We have a number of kind of core objectives. The first is to grow a world-leading UK-based research network around the topic of thermal energy, and that isn't tied to any particular objective, in the sense that it's just supposed to support net zero carbon heating and cooling, and also it's for residential, business and industrial sectors. It's not tied to anyone specifically. We aim to bring together different kind of groups, whether they're technology developers, end users, social scientists and policymakers, and we're trying to get them to talk together, because this is a whole challenge. it's an integrated solution that will lead us to a net zero in heating and cooling. And we'll do that through a number of routes. We're talking about sandpits, workshops, opportunities for secondments and studies, and wider engagement activities. We also aim to try and do some cross-cutting and make some cross-cutting challenges via research and developing some consensus around them. And then we have some flexible funding. I guess this last point is really we have some funding to support doing these secondments, support doing some startup research activities and so on in order to do that, and also how to upskill our early career researchers so that we can keep the ideas coming. Across our 5 core themes, and these were constructed around all of the different areas that are relevant, and they're quite general. But the first one is really around what we've called primary engineering technologies and systems for decarbonisation. So this key theme is on the technical end of the scale. This is about heat pumps. This is about hydrogen heating systems and so on. The second theme here is underpinning technologies, materials, control, retrofit, and infrastructure. So these are the parts or the systems that enable you to heat or cool your home or your business. Third theme is around future energy systems and economics. So how does this fit in with the whole wider net zero challenge? Where does the energy come from for our next generation of heating systems and cooling systems? And how much will it cost? And how will that be enabled? And then themes 4 and 5, perhaps slightly less technical and more social science based. The first one being societal impact and how do end users perceive our transition to net zero, and how do we build those into our thinking. And then number 5 is more of a top-down, how do we support policy in making and enabling this, and how do we support leadership to make some of the difficult decisions that may need to be made in order to get us to net zero within the expected timeframes. Now, all of this will be done through the network platforms. We're planning to help do this through what we originally put in was 20 co-organized events, which would be conferences, sandpits, trainings, and workshops. This was obviously pre-COVID, so some of this is changing a little bit as we talk, but to give you an idea, there will be a lot of events in and around this topic. We will facilitate this through some secondments and travel bursaries when travel permits. And as I mentioned, there's some feasibility funding budget available, and that will be announced in due course. And we're also developing technology roadmaps, which should help us explain what the challenge is to a wider audience. Now, this is kind of my last slide before we start moving on to the talks, but we've got a number of different routes to push outreach. The best one and the most informed one is the Net Zero Research website. If you go to there, you can sign up and then you can get on the email list. If you're on the email list, you know when activities and they'll be pushed into your inbox. You can always go there and find out when the next event is. Over the last few months, we've been doing lots of webinars and so on. So, and you can also go back and look at the videos because everything was recorded, and that's all available on those different platforms. So now coming really on to the today. Today's topic is heat and energy systems. We're not sure if this was by design, but today is also Earth Day, and that today is a day to reflect on what we can do to help restore our planet. And this is obviously a very timely combination because heat and energy systems is possibly the UK's biggest challenge for reaching net zero. And we've basically structured today into 3 parts. Session 1 will look at energy systems and geothermal opportunities. So we'll move on to the first speaker, and I'll introduce first Professor Peter Taylor from Leeds University. He holds a chair in sustainable energy systems. His research is highly interdisciplinary, combining technical, economic, and social insights to explore how to accelerate the transition to sustainable low-carbon energy systems. Peter is a member of a large academic research collaborations and has been involved in the UK Energy Research Centre, the Centre for Research into Energy Demand Solutions, the Supergen Energy Networks Hub, and the ESRC Centre for Climate Change, Economics and Policy.
So thanks very much for that welcome, and thanks for the invitation to speak. So yeah, the topic that I was asked to talk about was energy systems and the implications of decarbonising heat. And I've interpreted that quite broadly. I saw that I was first on the agenda, so I thought I would provide a little bit of a kind of introduction perhaps to today in terms of the heat decarbonisation challenge, some of the opportunities, and I think very definitely the fact that in looking at this we need to take a whole system perspective. And towards the end of my presentation I want to briefly touch on the fact that this is not just a technical challenge, but there are many other elements that we need to consider as well. So that's what I hope to get through in the next 20 minutes or so. So first of all, the decarbonisation challenge. So I've put together this chart showing where the greenhouse gas emissions in the UK come from, according to some broad sectors. And you can see, if you look at that down there on the left-hand side in blue, with a share of roughly 33%, is the emissions that arise from heat. So actually, if you break it down like this, then heat is the largest single contributor to greenhouse gas emissions in the UK. And I think it's pretty obvious, therefore, that there's no chance of getting anywhere near net zero unless we are able to substantially decarbonise heat. So looking in a little bit more detail about where that heat is used and the sources, the fuels that provide that heat. So if we look at end uses of heat, we can see that much of it goes to space heating, and I guess together space heating and water heating definitely dominate. And within that, it's the domestic sector that's the main end user of that space heat. But there are also important uses of heat in industry, some of those being at much higher temperatures than one would need for space heating. So although a lot of the focus on decarbonising heat, I guess rightly, is around space heating and domestic and perhaps commercial properties, we mustn't forget that we also need to do something about decarbonising the heat use that is in industry. And then if we look at the fuels that are used to produce that heat, then I don't think anybody's going to be surprised to see that around 2/3 of that comes currently from natural gas. Electricity also makes an important contribution. I was quite surprised actually to see that oil still makes a large contribution, which I guess must be for off gas grid properties. And there is some bioenergy and waste use, but really to date, low carbon technologies are not making a significant contribution towards heat provision in the UK. But that obviously has to change, and that has to change pretty quickly. I think the other thing to keep in mind when we're thinking about the decarbonisation of heat is about the pattern of heat over time, over the months of the year. So this is a chart, a well-known chart that was created by Grant Wilson, now at Birmingham University. And what it shows in blue is total gas demand in the UK, much of which is for heat. And we've also got, for comparison there in red, electricity. And the thing to notice, I guess, which everybody probably knows, is that gas demand is highly seasonal, because heat demand is highly seasonal. So we have this challenge that we need to have a decarbonised system which is able to cope with the peaks and troughs in heat demand. So that's when we're thinking about technologies and thinking about the system impacts, that's an important consideration to keep in mind. So, okay, so what are our heat decarbonisation options. And I guess in doing this, I'm always bound, someone's bound to tell me that I haven't divided it in the right way, or there are options that I've missed. But here's my kind of take on the situation. So we can change fuels. We can move to electricity. We could use hydrogen. We can use biomass, and we can use solar. Before somebody points out to me that neither electricity nor hydrogen are primary sources of energy, it's clear that those carriers have to be generated from primary sources. So the extent to which both electricity and hydrogen are actually low carbon or can contribute to decarbonisation very much depends on where they come from, where they're generated. So that's another important consideration from a system perspective. Alongside the change in fuels, we can change the technologies. We can have individual technologies, as we've mostly got now with gas boilers. We could move more substantially towards communal technologies, so using things like district heating. And in terms of the individual technologies, we're going to hear more today about heat pumps. There are also hydrogen technologies. Boilers, I guess, would be the most obvious, but there's some interest as well in things like fuel cells. There may be renewable technologies, biomass, combustion, solar, that has a role to play. And as I say, there's of course the possibility of expanding the role for district heating, which itself would use some combination of the technologies and fuels which are shown on this slide. Or I suppose the other thing that we could do is we could just carry on with natural gas, but at least in some applications it might be possible to capture the carbon dioxide that's released and then sequester it, and that might be an option for particularly in industry, I guess, or in situations where we're using large amounts of gas. Probably harder to imagine that that's going to be an option for domestic homes. So then let's start to look into a little bit more detail into some of these options. So I've borrowed this graphic from an Element Energy report, really just because it starts to show the complexity that we get into, even if we're considering one of the options. So clearly one thing that we could do would be to convert all our heating over to some kind of electricity. And as we progressively decarbonize electricity supply, so we would therefore progressively decarbonize our electricity, our heating system as well. And so obviously we could have direct electric heating, which is down the bottom, but what is gaining a considerable amount of interest is the role of heat pumps because of the efficiency gains of using that system. However, we know that heat pumps prefer to operate continuously. They typically operate at relatively low temperatures. And so there's questions around, well, are they actually going to manage to meet the peaks that we see in demand? And so therefore the hybrid heat pump option, the second one down there, is also gaining interest. And we can see, even if we're just looking at the sort of the end user side of things, we've got options in terms of air source or ground source heat pumps. And someone might point out we could also use water as a heat source as well. These can be individual heat pumps. They could be bigger heat pumps in a communal system. Most heat pumps are sort of in the, 30 to 45 degree temperature range, but there are also high temperature heat pumps which can go to higher temperatures, maybe 80 or even 90 degrees. And then there's the question also about whether we would need to combine these with some kind of energy storage, whether that be hot water or a newer design of thermal storage, using latent heat or something else like that. So already we can see that there are kind of system questions which are coming up when we're only thinking just about the end use, never mind thinking about all the implications upstream of this. And another interesting question is, as I sort of alluded to, is actually how are heat pumps able to meet demand? Well, luckily there's a recent paper that has looked at this, which I've taken a couple of graphics from. And it's quite interesting in this paper, which has used empirical data, so actual real data from people who are using heat pumps currently, as well as those that are using gas boilers, to see how the move from gas boilers to heat pumps has actually changed people's patterns of how they heat. So you can see there on the left-hand side with gas boilers that some people, or most people, switch them on just during the day. Many people sort of have a bimodal operation, so they switch them on in the morning, then off in the middle of the day, and then on in the evenings when they come home. And there are a few people who have those gas boilers on continuously. But then when we move to heat pumps, we see that there's a far greater proportion of people who are actually using them continuously. As I say, that's probably the mode of operation that they prefer. They produce relatively low temperature heat, so they're less good at producing a big injection of heat into a house like a gas boiler has. So along with a change in technology, we may end up with a change actually in the pattern of the use and the way that we actually heat our homes. And this has quite important implications for the profile of heat demand over a day. And so this chart shows a number of different things, but broadly speaking, what it's arguing is that it's probably not going to be the case that heat pumps have to mirror the pattern of demand that we're seeing with gas boilers. So the pattern of demand with gas boilers, there was a famous paper by Sansom from Imperial College back in 2014, which said, well, heat pumps are going to have to meet this really peaky demand, and that's going to be difficult. This paper argues that in fact the demand pattern is likely to be smoother for a number of different reasons. But nonetheless, there are peaks and troughs, and nonetheless, as you can see there, up to 150 gigawatts of heat demand may be needed at any one point in time, which is not an insubstantial additional load on the electricity system, as we will see. So moving on, just to sort of reflect on some of the system impacts, I've taken this work. This is work that was led recently by the Net Zero Infrastructure Industry Coalition, which the University of Leeds had a small role in. And this is suggesting that in this electrification kind of scenario, we might need up to 400 gigawatts of electrical capacity. So that's something around about 4 times what we've got now. And you can look at the details of where they think that might come from, substantial increases in wind and solar, but also thermal plant, nuclear as well, and also upgrading the electricity network and the need for storage. So big changes to the wider electricity system in order to deliver on this kind of scenario. And I'm not saying that this is right. I'm just saying that one has to think about the implications, the broader implications, when we're considering if we're going to have a big rollout of heat pumps. Moving on to hydrogen heating technologies, again, a range of different technologies that we can use. We can use boilers, either sort of conventional direct flame combustion or maybe even catalytic boilers. We can use fuel cells. We may be able to use a gas heat pump using hydrogen. And again, we could, at least in theory, use hydrogen in district heating. Again, there's a huge system behind delivering that hydrogen to our homes. There are questions around, are we better off using hydrogen actually for domestic heating, or would we be better off using it in a different application in industry or in transport, for instance? There's then the question of how that hydrogen is going to be distributed. I mean, it can probably go into the distribution network, but in terms of transmission, are we going to try and repurpose the existing gas transmission network, or will we need a new dedicated hydrogen transmission network? Importantly, where's that hydrogen going to come from? I think many people think that probably steam methane reforming is going to be the most likely, of natural gas is going to be the most likely initial source of large quantities of hydrogen, but eventually I think most people would hope that we could move to renewables, and then there's a lot of questions on the amount of renewables that we might have and what that does again to demand for electricity, and of course there may even be the possibility of importing that hydrogen from other countries, including the Middle East might move away from oil and move into hydrogen production. Who knows? But lots of really important system questions around the provision of that hydrogen as well. And again, taking a graphic from that same Net Zero Infrastructure Coalition. So in this hydrogen scenario, we also have a lot more increase in electricity. So 250 gigawatts of electricity alongside more than 100 gigawatts of hydrogen production if we're going to convert something like 15 million homes, which is what they've got in this scenario. So again, this is not to say that this is the right answer, but just to point out that are big upstream system questions which will need to be addressed if we were to go down the hydrogen scenario route. So how do these kinds of pathways compare? And so I took this chart from a report by Imperial College, and I think you've got Danny later in the afternoon who I think worked on this, so probably can answer any detailed questions. But this looks at a number of different scenarios. It looks at a hydrogen scenario, an electric scenario, and a hybrid scenario. And it breaks down where the costs fall. And I was looking at this chart in some detail, and it's really interesting that sort of a third to a half of the costs that are involved in each of these scenarios fall sort of outside the direct technologies that are involved. So there are various forms of network and other costs associated in the wider system. And so, as I say, in evaluating these various options, it's really important to take that system perspective, because if you don't, then you'll miss a lot of the important impacts and a lot of the important costs. So I just wanted to also mention industry, because as I say, there are some important uses of heat in industry, often at higher temperature. This is a chart taken from a US study. So on the left-hand side, you can see the kind of temperatures that a number of different industries are wanting, and then the bars show the kind of potential temperature delivery from a number of different options. In the middle there, we've got both electricity and hydrogen, which can, at least in principle, deliver quite high temperature heat if that's needed. So those two options could indeed be also used to decarbonize industry, moving away from natural gas for heating into perhaps electrification or hydrogen. And of course, in addition to that, you've got the possibilities, I said before, of using carbon capture and storage, so keeping with natural gas, but then capturing the carbon and putting it somewhere. If we look at the government's recent industrial decarbonisation strategy, I think one of the challenges that they identify is that although around about half our industrial emissions are in so-called clusters, so might be amenable to things like CCS and hydrogen, there is also about half the emissions in dispersed sites. And I think it's still an open question the extent to which hydrogen and CCS might be available to the myriad smaller sites which are distributed across the country. And indeed, if you look at some scenarios that developed for that strategy, the one on the left assumes national networks. So that basically assumes that you get network of CCS, either pipelines or trucking, pretty much everywhere, combined with hydrogen pretty much everywhere in the country. And then those are the decarbonisation options. And then the one on the right-hand side says, well, what if CCS and hydrogen is only available in clusters? And you can see quite a different pattern of reduction arises. So electricity, perhaps not surprisingly, plays a much more important role in the cluster one. So that's saying that if hydrogen and CCS is not available for much of the rest of the country, then maybe they'll have to use electricity instead. And as a result, the use of hydrogen goes down. Whereas if we manage to get these hydrogen networks pretty much everywhere, then hydrogen looks to be a promising option, and therefore we squeeze out the electricity. But again, big uncertainties on how the development of the wider energy system will impact decarbonisation of heat. So we've talked about the impact of heat on the wider energy system, but there's also trends in the wider energy system will also impact the kind of options we might have available for decarbonising heat. So I'm running towards the end of my time, so I just wanted to also stress that this is not just a technological issue. There are all these other factors that are shown in the boxes here. Institutions, which in this case means the sort of not institutions necessarily as in organizations, although they may be important, but more around the sort of laws and policies that are being introduced. User practices, we've already seen how they can impact have impacts on technology in the way that people are using heat pumps. We've got the business strategies that people are using, but also broader ecosystem and environmental impacts. So we've seen with things like the move to diesel. So people were encouraged to buy diesel cars, and then we said, oh yeah, but they're not very good for urban air quality. So there may be similar issues around some of the low carbon options that just because they're low carbon doesn't necessarily mean they're good on a broader environmental basis. So all these things will need to be taken into account. And I took this chart from another Imperial study, different group of people at Imperial back from 2016. And again, I'm not necessarily suggesting that this scoring is right, but what they have here is they've looked at hydrogen, they've looked at heat pumps, and they've looked at district heating, and then they've scored those on a number of different metrics. So the cost and impact of decarbonised heat supply, the cost and impact on networks, the cost and impacts on customer premises, and the need for new regulation. And you may disagree with the scoring that they've used, but basically you can see here that it's not that there's a clear winner. You know, there are reds and greens and yellows for across the technologies. So it's not obvious, you know, which direction we will be going, and it may be a combination of these things. And I think more research is still needed to really tease out some of the intricacies and some of the details behind these costs and impacts. And so finally, I just wanted to sort of reflect, you know, what is this challenge, and do we actually need to be thinking about a more systemic change? So certainly not a new idea is the idea of what if we were to deliver heat as a service. So rather than buying units of gas, what if in some way we could buy, you know, units of heat or levels of comfort or temperatures in our homes? What would that deliver? Would that actually transform the way that we are thinking about the whole heat problem and get away from this idea of buying sort of heat, the fuel as a commodity, and think about more about the service that it delivers? Well, there's again been a recent paper, luckily, that has looked at some of these issues, and so I took some of their analysis and put it against the kind of issues that I'd highlighted in the previous slide on using the sort of user practices, institutions, technology, and business strategies kind of framework. So in this paper, they identify in terms of user practices a bunch of issues. I think one of the really interesting ones is around energy contract lengths. The fact that if you're going to have heat as a service, then you'll need to have a longer contract length, so you won't be able to have the switching that we do now. They also highlight the importance of things like energy behaviours and the willingness of consumers to withstand disruption. On institutions, they talk about, you know, a lack of clear policy in a number of different areas, and rules around regulation and switching also come up there as well. In terms of technology, it's interesting that most of the things that they highlight here are not about heating technology issues, but they're all about the IT systems and data security and cybersecurity and all the rest of it, as well as whether we actually have the skills base to move towards that. So it's interesting that some of the barriers to some of these options may not actually lie in the energy field, but may lie in IT and data. And then finally, with business strategies, lots of interesting questions about who owns the assets. The fact that one would want to combine an upgrade to a heating system, at least potentially, with an upgrade to the fabric of the building, which I haven't really mentioned, but I think that's extremely important, and also extremely important in terms of the knock-on impacts on the wider energy system. Actually, how much electricity and how much hydrogen will we need to be delivering? The question around finance and investor confidence. So lots of issues here, but I think really, instead of thinking just about whether we're going to take out one technology and put in another technology, I think really worth thinking about whether we need to rethink entirely how we're delivering heating and of course potentially cooling as well. So and finally, just basically to say, heat is a big challenge. It's an important source of greenhouse gas emissions. We've really got to get on and tackle it. There are a range of low carbon options. None of them have a particular stranglehold in the UK to date, and I think it's still unclear which direction we're going to be going. When we're thinking about that, we really do need to have a whole system perspective when we're just thinking about technical issues, but also not forget that there are a whole myriad of non-technical issues which will also be extremely important to think about. And I personally think that this idea of delivering heat as a service is something that we should be sort of foregrounding as we're thinking about this transition, because that also enables us to factor in the role of energy efficiency and fabric upgrades, so that we make sure we're not just focusing on delivering as I say, changing one technology for another and just one fuel for another, but we're actually thinking more about the service that we want from heat. So thank you very much.
Next up is Professor John Gluyas, I guess is just connecting in, as you can see. John is a geoscientist and is the current executive director of the Durham Energy Institute. John began work with BP, working around the globe from exploration to production geosciences. John formed Acorn Oil and Gas, the first company ever to redevelop a completely abandoned North Sea oil field. And then he left the industry to take up a newly sponsored chair in geoenergy and CCS at Durham. John's research since joining Durham has covered enhanced oil and gas recovery, including CO2, carbon geostorage, CCS, geothermal energy, human-induced seismicity, and using the skills developed in industry, lithium, helium, and now golden hydrogen exploration. So John, are you ready?
Thank you very much indeed. Thank you also to Peter for really setting the scene in some ways. I should add that living slightly off grid, our oil has just arrived. So I'm one of those customers who unfortunately has to rely upon oil, Peter. So what we heard from in the last talk was a very good description of some of the problems associated with delivering heat, and I agree entirely with the thinking of heat as a service. But let me look at things slightly differently in terms of the heat which exists within the earth and how we might use that. And the other thing I want you to think about is that heat is the sort of back end of every energy transition, either consumes or liberates heat. And in that sense, there are lots of opportunities for using different processes to harvest heat, some of which marry quite nicely with the geothermal aspects. So if we go right back to the sort of fundamentals, we are dependent upon the sun, the earth, and a little bit of the moon for our total energy, unless you're going to start potting stars into black holes and somehow harvesting the gravity waves thereof. You're really limited to this suite. And that covers light, heat, materials, of course, the materials we use for energy, and nuclear energy, gravity processes, and so on. But the one I'd like to highlight today is geothermal energy, the heat of the Earth. Now, the Earth's about 4.5 billion years old, thanks to some dating originally done back in the 1920s by Arthur Holmes here in Durham. And we're in pretty good shape because as far as sustainability goes, the heat source, which delivers our Earth and means it's still hot today after 4.5 billion years or so of existence, is still 85% of that intact. And basically it's the decay of nuclides like uranium and thorium coupled with the original heat from condensation of the Earth, which gives you the that heat source. Geothermal energy is excellent for both heating and cooling, and in some instances, power generation. And following on from some of Pete's stuff, it's also rather good for base load. Unusually, there is no, there's no cartel that could monopolize geothermal energy in a global sense. It might be slightly hotter in Iceland or California or Italy in terms of beneath the ground, but every nation on Earth can develop geothermal energy. So it doesn't travel well, but it doesn't travel well. The other neat thing is we don't require some of the exotic materials, such as the rare earth elements, to build a system which can provide heat to you. And because it's basically within the Earth, we have a small surface footprint. There are some challenges, particularly if you're using very high temperature geothermal. There may be some induced seismicity. And the other point, and that this marries quite nicely with the last talk, there are low margins in terms of, a barrel of oil will always be much more valuable in energy terms and thus financial terms than a barrel of hot or even tepid water. Nonetheless, because we use heat, our radiators perhaps run at 60 degrees centigrade, but really we're only sufficiently concerned with keeping warm or keeping our bath warm, so we can run at these lower temperatures. Now, if we look at the relative growth of geothermal energy versus installed capacity for a broad spectrum, this is globally, of renewable energies, we can see that over the period 2010 to 2020, there's been a 100% increase in renewable capacity, but we've only seen a 40% increase in geothermal energy, and one needs to ask the question why, although this particular chart emphasizes the use of geothermal energy for power generation, which is hot stuff, rather than the cooler stuff, which I will talk about now. Now, one of the key things about geothermal energy, and this is again related to high temperature geothermal rather than low temperature, the figures for low temperature are almost zero, but the carbon emissions associated with the operations are much, much smaller. And here we have some figures coming out from the Department of Energy in the USA, just comparing the emissions associated with coal and gas-fired power plants, both in terms not just of carbon dioxide, but also some of the other greenhouse gases, SOx and NOx, much, much lower indeed. And given we have this, we're not able as humans to cool the earth. We can mismanage the way we deliver heat, but we're not going to cool the earth, so we have a sustainable supply. Now, what I'd like to do now is just flip a little bit and start to think about the UK within this context. It doesn't come to mind as a hothouse for geothermal energy, but you might be surprised to see what we have. So, if we think about the way in which we can use geothermal energy, there are a number of possibilities, and we've heard mention of heat pumps. Basically, if we use a little bit of warm water from the earth on the inlet side of the heat pump, we don't have to use as much power to upgrade that heat as if we use cold water. And so, for example, just looking at a electric heating system, if we swap that out and use low-grade geothermal heat with a heat pump, we drop our electricity demand by about 75% or so. And this heat generation, you can use either pretty tepid stuff or indeed much warmer heat, depending upon the process that you're interested in. And then there are ways in which we can generate power from that geothermal heat either directly, because there's sufficient heat in the Earth's surface to cause injected water to turn to steam, or naturally flowing water to turn to steam, or we can generate it through some kind of combined cycle, which allows you to utilize much lower temperatures. And if we think about the sort of systems which exist and are available to us, in the UK, there are a whole suite of things. I'll mention abandoned coal mines, I'll mention oil and gas fields, and I will also mention some of the deep saline non-potable aquifers which are available to us. So as we saw in the last talk, about half of all the energy used in the UK is for heating. And a little bit, but not much, for cooling, although that could change as climate changes advance. And 77% of all the heat comes from burning fossil fuels, either directly, as was shown in the last talk, or indirectly, because we generate power by burning gas, and that's a very overall inefficient process. And again, as you saw, a huge chunk of that ends up as greenhouse gas emissions. First of all, let's take a look at the low temperature end of things. Coal mining provided the growth, the industrial revolution for the UK from the 17th, principally 18th century and beyond. We peaked in coal production in about 1911 with 300 million tonnes mined. And indeed, the whole of County Durham relied upon mining for its income for the best part of a century. Indeed, the miners of Durham, despite only representing 0.5% of the population of England and Wales, mined about 15% of the coal. And there are now some 23,000 abandoned mines in the UK, almost all are coal mines, and almost all are now filled with water which is naturally ingressed as the mines have been abandoned. Indeed, in some areas, it's such that because water levels tend to build up naturally, the coal authority is having to pump out those mines to maintain safe water levels. And in doing so, it's currently emitting 80 megawatts of heat every second of every hour of every day. A phenomenal amount of heat when you think about it. Now, we can use the water within those mines, and there are already several operational systems and more that we're bringing along in the northeast of England and elsewhere to provide large-scale, low enthalpy, low temperature heat. At the moment, there's an operational scheme in Gateshead, which produces about 4 megawatts of heat and heats the largest wine warehouse in the UK. But we're seeing other developments for housing estates, potentially for heating a swimming pool, which would be heated, if you like, heat coming from Mother Earth, and so on and so forth. The emissions here are negligible. But you don't need necessarily to use the mines simply for abstraction of heat. We can also put heat back into the mines, something which has been done at large scale in Heerlen in the Netherlands. So, for example, you could gather solar thermal heat during the summer and inject it into the, if you like, as heat into the mine systems during the summer, and then harvest that in the winter. They're extremely responsive. And you saw Ian Grant Wilson's chart on the last presentation, responsive in that sense as well. So we could meet that kind of demand. And of course, the other key part of this, particularly when thinking about this low enthalpy systems, are that the UK, for the most part, built its towns and cities on coalfields because that's where the work was. So currently, 25% of all housing sits above coalfields. Almost all entirely, with almost no exception. Those have now been abandoned and are available. The scope for heat storage in mines alone is around about 36 billion gigawatt hours. But it's not just mines. A couple of years ago, well, 2011, with Newcastle University, we drilled in central Newcastle and proved the geothermal gradient there, proved the heat potential with a research well into a deep saline aquifer. And these saline aquifers, again, span the UK, throughout the central belt of Scotland, the northwest and northeast of England, down the east coast, the Worcester Graben adjacent to Birmingham. The temperature at, say, 5 kilometres beneath Crewe is about 100 degrees centigrade. And we know we can transmit fluids through these, harvest the heat. And then the last item, the sort of big ticket power generation item for geothermal onshore in the UK is to drill things like deep granites. You may have heard that hitting the news recently that the granites in Cornwall are being drilled both in the Eden project and in United Downs. But some 10 years ago, we drilled in the Weardale granite several research wells. And again, they're demonstrated not just the heat, but the ability to abstract heat as water in those systems. So the opportunities are phenomenal. In fact, really the only major population centre in the UK that doesn't benefit from either flooded coal mines or basinal systems is London. And there's plenty of hot air in London anyway. And I mean that in a sort of sincere way. We can also heat London using things like the heat in the tube systems and thermal piles and so on. But taking this in the last few slides a little bit further forward, we have an oil industry which has powered and financed the UK for about 50 years. We became a net exporter as Margaret Thatcher walked through the door of number 10 in 1979 and became a net exporter of oil and gas, importer, I should say, of oil and gas as Tony Blair left in the early part of the last decade. But what we've done there is mine oil and gas from the fields. There's a huge amount of heat contained within those fields, some of which can still be accessed. And the chart on the left-hand side just shows the potential for producing power from co-produced fluids. So most of the old oil fields co-produce copious amounts of water, maybe 20 or more times water than they do petroleum. This will help decarbonize the system by being able to produce power. And these are shown in megawatts from these various fields. But possibly even more exciting, and coupling with what you heard in the last talk about carbon capture and storage, we need to remove carbon from our systems as carbon dioxide and bury it deep, potentially in old oil and gas fields. And in doing so, we have the opportunity then to create carbon neutral or carbon negative CO2 powered electricity generation systems offshore. Unlike water, we don't require a parasitic load to put the dense phase CO2 in the ground. That will circulate freely between the deep ground and the surface, drive a turbine, and therefore generate electricity. There's a real chance, notwithstanding some big technical hurdles to get over. We're working with ETH Zurich and Potsdam in Europe and Siemens and Shell to be able to turn what were carbon intense petroleum systems into carbon neutral or carbon negative power generating offshore systems. Circular economy, phenomenal potential to decarbonize heat throughout the UK. We could service our system entirely, if you wish, for at least 100 years, even with profligate use, and with almost sustainably forever without proper use. Power yet to be done. And, great opportunity to really hit that greenhouse gas reduction targets. Thank you.
Brilliant. Thank you, John.